we're going to do our next video for our Earth history. So again, we're just up in our nice Google Classroom. If you click on here in our instructions, and we are going to do this notes right here, the universe, day 19. So it is right here. And what we're going to talk about today are different ways that we know how old the Earth is. So we'll get right into this. So first, some of our vocab terms. We're going to talk about relative age versus absolute age today. We already know paleontologist, right? There's someone that studies the fossils. We're also going to look at index fossils and trace fossils, as well as what half-life is, and extrusion, intrusion, fault, and outcrops. And we're going to look at all of those today, so it's going to be a busy day. Again, this is all in Chapter 8 of your book as well, so feel free to look through that as well for all of this. So when we look at age dating the Earth, we've got two different ways. We can go absolute age dating, and that is actually looking at very precise age of rocks and doing these different techniques. And that's what we're going to talk about in the next video. So for this video, we're going to talk about relative age dating, because this is something really actually pretty easy that you can do just from having the knowledge in your head and using common and logical thinking skills. So we're going to talk about these different principles and laws, and we're going to look at all of this for this notes, and we'll look at this in the next one. So first, we're going to know the difference. What's the difference between relative and absolute? Well, if you think about it, absolute means I know exactly what age you are. Think about it. If I knew exactly which day, time, and year that you were born, I would know your absolute age, right? But relative means I know kind of the order in which your guys' birthdays are, but I don't know the exact days. Maybe just based on you guys are all freshmen, so I know how old you should roughly be, 13 to 14-year-olds. But if I put you right next to a senior, they should be older. They should be more around 17, 18. So I know relative that you guys should be younger than the senior that's walking down the high school hall, right? So I know the order, but not the actual date. So other examples, sometimes I get a little bad with some of my history, and you're like, oh, Civil War, when did that take place? Well, I can't remember the exact date, but I do know that it happened before World War II. So at least I kind of put it in a little bit of a context of I know the order, but not exact. Same thing, I know that the actual bedrock of Montana had to form before the Cordilleran ice sheet came along during the last ice age and completely reshaped our state. So I know the rock had to be here before the ice age. Comparatively with absolute, Civil War, boom, 1861 to 1865, World War II, 1939 to 1945. Okay. Yeah, I said the same thing. I just couldn't tell you the actual date. So I gave you the relative age. And that's the great thing about relative is you just have to know kind of logically what actually happens without giving exact information. So types of ways to do our relative age dating. Things we have to know. First is the principle of uniformitarianism. The father of all geology is a Scotsman by the name of James Hutton. In the 1700s, he actually used to take people up to a beautiful bluff on the side of Edinburgh Castle, and you could actually see some old fossil remains up there. So even during that time, he would take nice little geology field trips, if you will, and his kind of famous quote is, "The present is the key to the past." And essentially, this idea is the one that shaped all of geology, saying whatever processes that we have today, do we know that we have earthquakes today? Do we have volcanoes today? Do we have erosion taking place when it's super windy outside? Absolutely. So all of those same processes that happen today have also happened in the past. So that leads us into, we know what happened in the past because it's the same things that happened right now. So with that, we can actually turn our attention and look at something like the Grand Canyon. Boom, you see this huge canyon. If we could go there, it'd be such a blast because I could show you all the different layers that you can see, and it's like looking through the pages of a book of the past million years. It's amazing. So when we look at this giant canyon, we can use something called the principle of superposition, and that states the oldest rocks should be on the bottom. Pretty easy. So oldest stuff is on the bottom, the youngest rocks are on the top. Same thing if we looked at this little nice cross section. When we see these gray ones with the little lines going through, this typically means shale. So remember our little mudstone. When we have these little bricks like this means limestone. They're ancient coral reefs. So one thing we should be able to tell is on this cycle right here, boom, here's the oldest one. It's all the way down at the bottom. And these guys should be younger at the top. Didn't have to know exactly, so I just know relative that this guy has to be older than this guy. Even this fossil right here has to be older than this guy on top. Super easy. So the next one is the principle of original horizontality, meaning all sediments are deposited horizontally. If we looked at this outcrop, it's in southern Utah down here, you can see all of these nice little horizontal layers going through, and that's called stratigraphy. You've got sweet lines right after another, and what's the principle states is that sediments are deposited in horizontal layers, and they are parallel to whatever surface they were deposited on. So in this, if you have this nice little just trough basin, and you can think about it, you could go pick up a thing of sand and go toss it into the river or the lake. Eventually, that sediment is going to settle out, and it's going to deposit horizontally. You guys have seen this when you walk into the lake. All the layers are pretty flat. If the bottom of the lake is kind of odd-shaped, well, you're going to have sand that'll sit there and it'll still deposit, and over time, it'll eventually get right back into this nice little horizontal layer. So pretty simple. All things deposited horizontally. You can also have beautiful things called ripple marks. So this is out on the coast. Shout out to both Jack and Drew. They're probably having fun playing with this right now. But what they're seeing is ripple marks right on the beach. So you can see the little, you can see the little knife and now the little keychain right here. So if we see ripple marks at the coast right now, and we go hike up on Mount Jumbo in Missoula and we see the same thing on the rocks, how do ripple marks form? Well, you have to have some moving water going over some nice sand or silt, or even some clay. But it will produce these beautiful ripple marks. So we know when this rock was physically created, it had to be close next to some water that allowed the movement of water going right over it. Maybe not always water. You can actually have ripple marks that are deposited in sand dunes. So you can get it from wind as well, but most commonly in water. So we know that this rock, even though it's on the top of Mount Jumbo, formed under the water somewhere. Same thing. Here's some mud cracks. This was just right outside the high school. So it's just after some rain, some really muddy, icky spot, and then you get these mud cracks. So all of the mud, now it's drying up, and it starts to crack. We've all seen it. So what happens if we go and see an outcrop and it looks like this? And this is a vertical wall too, by the way. Crazy, right? Well, mud cracks form the same way millions of years ago as they do today. So this all once had to be horizontally flat. It would have been clay and silt, huge rains, and then dried out. And then it had to have been deposited over and underneath a bunch of other sediments to kind of preserve it because it hasn't been eroded. So same thing. We can even look at nice little clay varves. And hopefully in the spring we'll get to go out on a field trip and look at some of these because we've got these right in our own backyard. So if you look, this is kind of what you see far away. But if you zoom in, you're going to see light sections, dark sections, light sections, dark sections. Well, each one of these, a light and a dark together, is actually 1 year. And the light layers are actually in the summertime. If you think about it, you've got a lot of creatures and fish and everything else kind of making all of the sediment really suspended up in the actual water of the lake, if you will. And then in the wintertime, most of those creatures either die out and the water is very still and it's very calm. So it allows all of that fine sediment and sand and clay to really sink down into the bottom. And then it gets really, really dense. So that's why it makes it a dark layer. And really, you can go back and you can count how many years Glacial Lake Missoula was here. You'd have to even core all the way down to even see the deeper layers. But we can still see them actually present today, which is pretty cool. Other things we've got graded bedding. So in this, if you come across a nice little outcrop and you see all of these giant pebbles, looks like almost a chunk of concrete, right? You've got all this big stuff down in here, huge sediment sizes, and it gets into fine sediments, and they look more like tiny little grains of sand, like sandpaper right in here. And this is called graded bedding. It goes from coarse to fine. So where do you get these? We get these deposited underwater, under really high flow, because it takes a long time for the fine stuff to settle out. You can also have different types of cross bedding. This is again in southern Utah. You can see almost the direction of these lines kind of change, right? Well, this actually shows that the direction of a river was actually changing. And so you can actually see some of the crazy uplift as well afterwards, because we know things were all deposited horizontally. So fluid flow. So now we know direction. That's pretty cool. The next thing we have things called unconformities. So what actually happens in an unconformity is typically you have a nice little lake. You've got all your sediments depositing horizontally, right? Then millions of years passed, the water is gone, and there's been some uplift. So see, all these once horizontal layers are now up on the surface, and they are all tilted up like this, okay? And then what happens is now it's exposed to the surface, so you've got all of this wonderful erosion that's taking place. You've got wind, water, everything, and it just makes the surface uneasy, right? You even have animals walking across it. Well, what happens is now all of those layers have been eroded. Then let's wait another million years. Maybe water comes back into this region, and now you've got more sediments being deposited. And so now you can see the sediments have deposited over horizontally. And what you have left is this crazy uplift and then this abrupt edge, this little erosional event, because now the actual strata above it is totally different. It is not the same age, it's younger, but this line right here is called an unconformity. It just means it's an erosional period. So even looking at some of these examples, something is definitely happening down here that's totally different than up here, right? It doesn't conform, right? So this is what is called an angular conformity, just like the one we looked over here. See, all of these layers are coming up at an angle. Even though they were once horizontal, now they've been uplifted, usually through plate tectonics and mountain block building. Then, when they were exposed at the surface, they eroded. They made little hills and mounds and everything else. But over time, that filled in. So now you've got all of this. So this part right here is called the unconformity. And if you look down here, you can see this disconformity. It still has horizontal layers, but they don't match up with the ones above. So that means there is something going on. If you look at this little section right here in the Grand Canyon, can you guys make out the unconformity? Can you guys see these? It looks like they're going up vertically. And this right here is actually some basalt. And then do you see this little section right in here? Almost like right where that shadow effect is coming in. And then you can see the horizontal lines going through here. So now you've got this horizontal strata right next to this vertical strata. This right here is the unconformity. Excuse me. So why do we do all of this? You can actually get paid big bucks to understand what actually happens if you want to work for oil and gas companies. So if we could take a nice slice of the entire rocks cross section of this mountain right here, we would see all these different types of rocks, and we've got them labeled out in different colors. And oops, let me move. Excuse me. We've got all these different ones in here. Okay. So things we need to look at are intrusions and extrusions. So intrusions. You're looking at just the volcanic magma that's getting caught up underneath. So these intrusions, see how A and B, they're both magma that's coming through, and it's essentially frying all the other layers of the rocks in this area. And these don't ever get up to the surface, right? So they're up underneath. Here would be the surface right up in here right now. So they are what you would call intrusions. Internal, where magma squeezes in between layers of pre-existing rock. So these intrusions, and if they did go out onto the surface, they would be extrusions like lava. These guys, as well as faults right here, they all have to be younger than these layers of rocks that they cross. And that is called cross-cutting relationships. So with that, think about it. All of this stuff had to be here first before the magma comes along and fries everything, or before the fault comes through and actually shifts everything. So extrusions, intrusions, and faults all are younger than the layers of rocks that they cut across. So if we were actually looking at this, you could tell me the relative age date of all of the rocks that are present in here. So we're going to do it together. So the absolute oldest, the oldest should be on the bottom, because that's what the law of superposition tells us. So the ones down here are the oldest. So 1 would be the oldest. Then it would go 2, then 3, 4, 5, 6. And then, do you see this unconformity? So after 6, there was definitely a little unconformity, but do we see A right here? Did A get stopped by this unconformity as well? So if I was putting this in a list, I'd go 1, 2, 3, 4, 5, 6. And then I would say A, because A is this intrusion. At the time, it was an extrusion. And then you had the unconformity come along and erode all of it. And then what happened is more sediment got deposited. So now you have 7, 8, 9, 10, 11. And through all of that, we had something else happen. So after 11, before the unconformity, do you guys see this fault right here? Did it offset 11? See how 11's up here, but then it's also down here? You see 10 is up here, and then it kind of shifts down, and it's over here. You can see that this fault offsets everything, including, look, all this stuff down here. So 4 kind of got shifted down, 3 got shifted, 2 got shifted, and 1. So this fault has to be the next one, because look, does this other intrusion go over top of the fault? So if this nice little intrusion goes on top of the fault, that means that fault was already there before. So the fault has to be older. So we would have had 7, 8, 9, 10, 11, and then the fault came along, and then the intrusion of B came along, And do we see how all of them actually got eroded? So then now comes the unconformity, because here comes that erosional event. And then after all of that is currently what's below our feet is number 12. So these actually can be really fun. They're right there on the back side of your study guide. So that last one is actually really fun. So you can even look at this guy. Can you guys find a nice little fault in here? It looks kind of little wicked. Almost looks like it's kind of coming vertical, but you kind of see this little splay here. See that offset and then down. So I challenge you guys can look at this even when you're driving anywhere. Look at old road cuts and stuff like that. You can actually probably see a couple of these little faults come across. And knowing that clearly these rocks here were here before the fault cut across them. So that fault is younger than the age of the rocks. So let's try this one. So which one would be the absolute oldest? So even though this guy right here is on the bottom, this is a little special case. This is how a lot of times geologists will write out what a magma little intrusion looks like. You see they kind of make like these little tick marks everywhere, and that makes it look like little crystals. So remember, if this intrusion has to be younger than anything it cuts across. So the absolute oldest, even though it's on a slant, would be J. So this blue layer right here, because it's actually on the bottom. Because remember, all things are horizontal, but it just got uplifted. So a J is the oldest, followed by K, because he's on top of him, and then F, and then H, and then we have B. Now what comes after B? Do you guys see this black one right in here? So this must be another little intrusion, and it's coming up. For some reason they made it old and black, maybe because it's just an older version. So now you've got G comes up. So see, he doesn't go up into E at all. So we've got J, then K, then F, then H, then B, and then G, and then we have E. But do we notice this black thing over here? Looks like it's a fault, right? Do you see these guys offset? So after E, definitely have this fault, and it's up underneath this I. So I'd say E, or then this fault, which is D. That's what that little label is showing us. And then, do we see these guys up in here? It looks like some of this magma kind of leaked out and made little bubbles up in here. So that means C was here before. And then after C came the I, because it cut across all of this, including the C. Then after that, A. So use all of this. Make sure if you've got any questions, please let me know. And do your best with the study guide for your relative dating.